All right, this is the first short answer paragraph question from Unit 3. I'm pretty sure it's the only short answer that they had from Unit 3. So our other problems are just going to be short FRQs. So it's not only chance to practice the paragraph, but we'll get lots of chances to practice the content. So a class of physics students is investigating projectile motion using a variety of equipment. Assume air resistance can be ignored in all cases. One group constructs a long ramp, as shown in ramp 1. In their experiment, they release a disc from the left side of the ramp, allow the disc to launch off the right side. The ramp is smooth enough that friction can be ignored. The left side of the ramp is supported by the top of a shelf, and the other side is supported by the top of a desk. The left and right sides of the ramp are at angles theta L1 and theta R, with the horizontal, respectively. The students release a disc from ramp 1 and measure the maximum height it reaches after leaving the right side of the ramp. The students then increase the angle of the left ramp so that theta L1 is less than theta L2, as you can see in the picture. They keep the top of the ramp against the shelf, as shown, so that the disc is released from the same height. Part A, will the disc launched from ramp 2 reach a maximum height that is greater than, less than, or equal to the maximum height reached by the disc launched from ramp 1, and justify your answer. So the answer for part A is that the maximum height is the same. And let's reason our way through that. The max height will be the same because what's happening in this problem is that gravitational potential energy is being converted to kinetic energy. And since the starting height and the final height are the same in both cases, there's no difference in our delta U, and delta U, and so there's no difference in our delta K, which means they have the same starting speed at the same angle. They're going to reach the same height. Now, you could also say that gravity is a force that's path independent or a conservative force or something like that, but it's all the same there, okay? Now, what's important is that we have the same Vy at launch. We want the same vertical component because that's what drives the height of the object. So wherever you end up, that's what you want to say. You don't want to say it's going to have the same speed there. You want to say it's going to have the same vertical component of the velocity because that's what determines the height. So rubric says 1 point for saying that they'll have the same speed at the top of the ramp because energy is conserved. So you get a point for saying that, but you get a second point for saying that the Vy is the same since they're launched at the same angle, the maximum height will be the same. So if you forgot to say the Y component will be the same and you just said the speed will be the same, you get one of the 2 points. But to get both points, you need to indicate that it's the Y component of the velocity that drives the final height. So 2 points for part A. For part B, it says, next, the students adjust the ramp into the configuration labeled ramp 3, in which the lowest part of the ramp has been shaped into a circular curve. Now, that's a different kettle of fish here, so that's what they're going to get at. Do you understand the difference between horizontal motion and circular motion? The lowest point of ramp 3 is at the same height as the lowest section of ramp 1. Both ramps are shown. On which ramp is the force exerted by the ramp on the disc at point A greater? So again, they're just asking you for the normal force, okay, the force exerted by the ramp on the disc. I don't think they'll ever say normal force because you know formulas for that. They want you to realize what the normal force is. So basically, we're going to figure this out. Is the normal force bigger on ramp 1 or on ramp 3? So on ramp 1, the normal force is just equal to mg. We've done this problem many times before. There's no other vertical forces. There are forces, well, there really isn't any net force in the x direction at all, but there's no net force in the y direction either, so the normal force is just equal to the weight. However, on ramp 3, the item is moving in a circle, so the net force in the y direction is mv squared over r, and that's directed towards the center of the circle, which is up. So what we have to say is that up minus down equals mv squared over r. our normal force is what's acting up, and gravity is acting down just like before, except for now up here, that was equal to 0. Well, not equal to 0, but Fn minus mg was equal to 0. But on ramp 2, we have this equal to mv squared over r. So the normal force is equal to mg plus mv squared over r. Now before, again, we've done this before, but before you just say, oh, well, the normal force must be bigger, we got to make sure that this is going to be positive, because if that's negative, well, then the normal force is smaller. So just a quick check, the mass is going to always be positive. Anything squared is positive, and then our radius is going to be positive. So this indeed will be a positive term. So the normal force is larger than the weight of the block, so it's greater than ramp 1. So, rubric, 1 point for saying that on ramp 1, the net y forces are 0, so that Fn equals mg, so 1 point there. 1 point for realizing that ramp 3 is a circle, so that there's a net upward force. As far as I'm concerned, that satisfies that category. And then for showing that the normal force is larger than the weight, so that the normal force is greater on ramp 3 than on ramp 1. That's your third point. So 3 points for part B. All right, so part C is your paragraph, and I really actually like this question because it asks us if we can translate what's going on a graph to what's happening in real life, because that's the point of making graphs. Another group uses a device that can launch a steel ball. The group launches the ball and it bounces off the ceiling, floor, and wall several times, though not necessarily in that order. Each collision can be modeled as elastic, and friction between the ball and the surfaces is negligible. The graphs above show the horizontal and vertical components of the velocity to the ball during some time interval in the ball's motion. The positive direction is taken to be upward. So during the time interval shown, the ball has 2 collisions. In a clear, coherent paragraph response, identify the times when each of these collisions occur using the times indicated on the graph, and explain how you know whether each collision is with the wall, the ceiling, or the floor. Okay, so let's look at our horizontal velocity graph first. I'm going to call the positive direction to the right for consistency. So what we see between 0 and time TA is that the ball is moving to the right, because I just called to the right positive. What happens at TA is that it hits something, and all of a sudden it's now moving to the left or in the opposite direction. So the only way that happens is if the ball strikes the wall. So we have the ball strikes, there's a collision with the wall at TA. And I can tell that because the direction of the velocity changed, right? The direction of the horizontal velocity changed, right? And that's all that happens with the horizontal velocity curve. For the rest of that time interval, it's moving in the negative direction, and we're done there. So what's happening in the y direction? Okay, so starting at t equals 0, the horizontal velocity is negative, and it gets more negative, right? Something happens at b, okay, because now the horizontal velocity becomes positive. Now they told us that up is positive, so we can tell that before time tb it's actually moving down, and at tb something happens to make it start moving up. That's pretty clearly a collision with the floor. So collision with the floor at tb. Right, and we can tell that because the y velocity went from down to up. And they specifically told us that the positive direction is taken to be upwards. So we know it's not the ceiling, we know it's the floor. So those are the 4 responses there. You get 5 points for part C. You get a point for realizing it collides with the wall at TA, and a point for indicating that Y. You get a point for realizing there's a collision with the floor at TB, and a point for explaining why. Then you get a point for a clear, coherent paragraph that addresses the question. So I feel like this is one of those questions that you look at it and you panic. You're like, you have no idea how you're going to possibly do this. But if you take it one step at a time and reason through it and ask yourself what the graphs are telling you, it's definitely doable. So that's the first question from Unit 3.